So this is the program for the lecture. We are going to present a number of experiments on an example of a model to see how these approaches can contribute to the understanding of the mechanical properties of graphene. So two different experimental approaches are used for the study of nanomaterial mechanical properties, two main approaches. One is the strain-strain methods, in which we are going to work in the limit of small strains and stresses not to go out of linear responses. The second method are vibrational methods, but this one is not easy to apply to graphene, so we will see it mainly in carbon nanotubes. In any case, we will see here, as in carbon nanotubes, and the main problem of all these experiments are that the uncertainties are very, very large. So we will need some contributions from models to try to understand some trends. Finally, in all cases, we will need to consider which is the thickness that we are going to take for the graphene foil. And usually this will be the standard value 0.335 nanometers if nothing else is said. This example, as the others present in the following slides, are extracted from the scientific literature. And you will find at the bottom of the page of the slide the corresponding reference. Here I present you a stress-strain study on exfoliated graphene. You remember that exfoliated graphene is the graphene obtained from this famous Scotch tape method of Game and Novoselov. So the sample can be considered in that case as a single crystal. In this experiment, exfoliated graphene was deposited on a substrate with holes, like you can see here. The holes are approximately 1 micrometer diameter. Then the stress-strain experiment was performed with an AFM tip, as is shown here, sometimes even up to rupture. As you can see in this curve, the stress and strain curve is not linear and needs to be fit with two parameters, E and D. The linear term gives us the in-plane stiffness C, which leads to an equivalent 3D Young modulus of 1 terapascal. The quadratic term D must not be confused with the bending radius. Here it is a quadratic term that goes out of the linear response. So finally, in this figure you can see the Gaussian fit of about 70 different experiments, so different holes, in which the AFM tip came and pushed the graphene, and you can appreciate the dispersion of the results. This is quite large, but the final result is within error bars equivalent to the in-plane Young modulus of graphene of 1 terapascal. So in this second example, a graphene bilayer foil is studied, and for this foil was suspended by etching part of its substrate and then leaving the graphene bilayer attached through gold electrodes. Then this allows to apply the difference of potential between these electrodes here and the silicon backgate placed below the membrane, and this polarizes the graphene membrane and allows for electrostatic forces application. So here you can see the sketch of the setup. In B you have an AFM scan of two suspended samples, and C is this beautiful same image of this bilayer graphene. D shows line AFM scans for different applied voltage, and finally here E shows you the deflection with respect to 0 voltage as function of the applied voltage. So using the Kirchhoff-Lowe theory for thin plates and considering a thickness for bilayer graphene of 0.68 nanometers, a bending stiffness of 35 electron volts was obtained. Again, you can appreciate the large uncertainties of the experiment. So in this example, we are going to consider the polycrystalline graphene. So the experiment is very similar to the first one, but here we are going to probe the resistance to fracture. So in this work, the response of CVD graphene, which is a polycrystalline form of graphene, is measured and compared to a single crystal graphene. So in the different holes, you can either find single crystalline graphene as here, or polycrystal graphene as here, and you can identify then grain boundaries with a given crystallographic angle between the two crystallites, which can be measured by electron diffraction. It is 30 degrees in this case. You can see the boundary here, and then the sample was propped up to fracture, as is shown here. So the authors studied the strength as a function of this grain boundary angle, and found that there is a strong dependence, not very much, up to 15 degrees, and then the fracture force needed to break the graphene foil increased with the grain boundary angle, reaching finally a value equivalent to single crystalline graphene. So this is summarized here, and what you can appreciate now looking to here to the boundary is that this boundary is made of the alternance of pentagons in red and heptagons in blue. So modeling allows also to study the mechanical response of graphene, and in this study the response to uniaxial strain of graphene applied either in this armchair geometry or in the zigzag direction as shown here was calculated. The obtained stress-strain curve is shown here, and if we make a zoom in the lowest strain region here, around here, for which applies the usual elastic theory, we see that the graphene response is independent of the orientation. We have the same response for the armchair and the zigzag configurations. This in plane elastic isotropy is what, as we saw in the previous video, is expected from symmetry arguments. We observe, nevertheless, that for large deformation some anisotropy can appear, and the most remarkable anisotropic response is in fact for strength. We see that in the zigzag direction the graphene membrane shows a better resistance to fracture. So in this table are compiled a number of values for graphene elastic constants, which have been obtained from different methods, experimental or theoretical. They are compared to the graphite elastic constants, which are in the first line here. And what you can see is that the best measurements that are the ones that maybe you can, or calculations you can find at the bottom, compare very well with graphene for the A and the C constants. That means for the in-plane elastic constants.